Hey, Finite Math fans. This is the lecture for Thursday, June 4th. I hope everyone's doing well today. Yesterday, we talked about Venn diagrams, and we drew Venn diagrams for A and B, sets A and B. We drew Venn diagrams for the complement of A. And we drew Venn diagrams for A union B, and we drew Venn diagrams for the intersection of sets A and B. And now we're going to talk about disjoint sets. Here's the definition of disjoint. Sets A and B are disjoint exactly when they have no elements in common. So if A and B are disjoint, no element of A is an element of B, and no element of B is an element of A. So in terms of intersection and union and so forth, we could say that sets A and B are disjoint exactly when the intersection of A and B is the empty set. Now remember, for Venn diagrams, in our Venn diagram of sets A and B, region 2 represents A intersect B. So here's region 2 right here. Region 2 is going to contain all of those elements that are contained both in A and in B. So let me shade region 2. And we'll note that A intersect B is region 2. Now, how does that relate to A and B being disjoint? If A and B are disjoint, then region 2 contains no elements. So let me write that down. So this is a good observation. If A and B are disjoint, then region 2, which represents A intersect B, contains no elements. Since that's the case, there's actually a special way that we can draw a Venn diagram for sets A and B if we know in advance that sets A and B are disjoint. If we know in advance that sets A and B are disjoint, and we're doing, let's say, a counting exercise or something like that, there's a special way that we can draw a Venn diagram for sets A and B that will indicate that sets A and B are disjoint. If we know in advance that sets A and V, if we know in advance that sets A and B are going to be disjoint, that is, they have no elements in common, then we can draw the Venn diagram for A and B this way. And notice in this Venn diagram, sets A and B don't overlap. So the way we've drawn the Venn diagram for A and B, there's no region 2. So we could label this as region 1. All of the elements that are in set A, but they're not in set B. We'll label this as region 3. All of the elements that are in set B, but they're not in set A. And everything that's outside of both of these sets, we'll label region 4. So we've drawn this Venn diagram in such a way that there is no region 2. So if we know that sets A and B are disjoint, they have no elements in common, this is the way that we want to draw the Venn diagram. Now, I guess there's also one more special case that we want to consider as far as Venn diagrams go. Okay, here's another special case involving Venn diagrams. And that special case is when A is a subset of B. Now remember what it means for A to be a subset of B. If A is a subset of B, then every element of A is also contained in set B. And so it really means that set A is inside of set B. So we'll call this set A, and this thing we'll call set B. We've drawn the Venn diagram in such a way that set A is contained inside of set B. Now, let me ask you this, just so that we understand these scenarios completely. Suppose that instead of A being a subset of B, it turned out that set B is a subset of A. How would we draw that Venn diagram? If set B is a subset of set A, doesn't that mean that every element of set B is also contained in set A? So it really means that set B is inside of set A. So this will be our set B, and the larger set will be set A. Now, I think it's about time that we did counting exercises. And in order to do counting exercises, we need to be reminded of one form of notation, and we need a special formula. And you know what? I'm not just going to give you the special formula. We're going to play around with things a little bit. And we're going to see where this formula comes from. First, the reminder about a special form of notation. This is the notation. Do you remember what that is? You might, we just saw it in passing, so if you don't remember what this is, don't feel bad, because we haven't done much with this yet. But we can think of the N standing for the word number. So this is the number of elements in set A. And so, in like manner, this represents the number of elements in set B. And finally, well, maybe not finally, this represents the number of elements in A union B. Yep, I have to introduce one more character. This notation represents the number of elements in the intersection of A and B. What we're going to be concerned about primarily with our counting exercises is this thing, the number of elements in A union B. And I'll give you a heads up. The number of elements in A union B also involves all of these other things. And we're going to see that in just a second. And the best way to see the relationship between all of these things is to draw a Venn diagram of A and B, where we don't assume anything about sets A and B. Okay, here's our Venn diagram for sets A and B. And we want to count the number of elements that are in the union of A and B. And remember what the union of A and B is. The union is all of those elements that are in set A, or the elements that are in set B, plus the elements that are in both of them. So if we want the number of elements that are in the union of A and B, then certainly we're going to count all of the elements that are in set A. And we need all of the elements that are in set B as well. Because A union B is the set of all elements that are in set A or set B. So take all of the elements in set A and all of the elements in set B and put them together. We have A union B. So we want to add the number of elements that are in set A plus the number of elements that are in set B. And now let's see, what would that be if we did it according to regions? Regions 1 and 2 and 3. Well, set A contains regions 1 and region 2. So, number of elements that are in region 1 plus the number of elements that are in region 2. Okay, now let's do B. The number of elements that are in set B, set B contains region 3 and region 2. So if we want the elements that are in region, if we want the elements that are in set B, then we'll count the elements that are in region 2, and we'll count the elements that are in region 3. So number of elements in region 2 plus the number of elements that are in region 3. And if we look at this, we might be scratching our heads just a little bit. When we take the number of elements in A and add the number of elements in B, look what we're doing. Did you see it? Yep, I'm going to put a great big oops here. We counted the elements in region 2 and region 3 twice. So we're not going to get the right answer. We counted that twice. We're going to get the wrong answer. Now, what does that tell us? It tells us this. If we try to compute the number of elements that are in A union B by taking the number of elements in A and adding the number of elements in B, we're going to get the wrong answer. Because when we add up the number of elements in set A and the elements in set B, we're counting region 2 twice. Because region 2 is in set A, but it's also in set B. So, first, let's observe that what I did is incorrect. This was our first attempt at counting the elements that are in A union B. And it's wrong. And what's wrong about it? When we use this formula to count the number of elements in A union B, we're counting the elements in region 2 twice. And by the way, just for future reference, in the Venn diagram, what does region 2 represent, if you think about it? Region 2 is the set of elements that are contained both in A and in B. But region 2 is the intersection of sets A and B, isn't it? So when we use this incorrect formula, we're counting the number of elements in the intersection of A and B twice. So here's how we compensate for that error. Here's our incorrect formula. In this formula, we're counting the number of elements in region 2 twice. So to make the formula right, we're going to subtract the number of elements in region 2. But again, remember what region 2 is? It's the number of elements in the intersection of sets A and B. Now, just for emphasis, I told you that this formula is incorrect. So I want to emphasize that this is correct. But we're going to rewrite this in its final form. That we're going to replace the number of elements in region 2 with the number of elements in A intersect B. And that's going to be the correct version of how to count the number of elements in the union of A and B. This seems like second grade math, but it's not. And in particular, when we do complicated counting problems, and when we do probability, this is going to be an important formula. This is a very important observation in probability. Now, let's write down the correct formula. We've seen the incorrect formula, the formula that we'd be tempted to use if we hadn't really thought things through completely. And we've gone to great lengths to brand that formula as being incorrect so that we don't naively make that mistake. We've seen why it's incorrect. Now let's write down the correct formula. Whoops. We want the number of elements in A union B, don't we? Okay, there's the correct formula. That's the formula that we're going to use to count the number of elements in the union of A and B. Now, somebody might say, well, suppose that sets A and B are disjoint, and there are no elements in region 2. Well, that's fine. This formula works in all cases. If there are no elements in region 2, that means that there are no elements in the intersection of A and B. So if there are no elements in the intersection of A and B, what does this thing equal? The number of elements in A intersect B. Isn't that going to be 0? So if A and B are disjoint, this thing is 0, and we're not going to be changing anything. So this formula works in all cases all the time. Okay. I really like this example because, when I go to a restaurant and I see things I like, I can't decide on one. And so I solve the problem by having both. Or if I see three things I like, I'll have all three. Doesn't say much for my self-control, but that's the way that I am. And some of us may be exactly the same way. Here's our exercise. On Fridays, Julia's restaurant offers two kinds of dessert, pecan pie and sweet potato pie. Of the 86 customers who had dessert on Friday, May 29th, 53 had pecan pie and 48 had sweet potato pie. So our question is, how many people had both? So here's what I'll do. I'll let A be the set of people that had pecan pie. We'll let B be the set of people that had sweet potato pie. And so let's see. A union B. Let's see, what would that be? That's all the people in set A and all the people in set B. So this is those who had pecan pie or sweet potato pie. Or both. Are we leaving anything out? Maybe this. A intersect B, what does that represent? Those who are in both categories, those who had both. Okay. We've identified all of the main characters. And here's what we want. The question asks, how many people had both? Well, that's the number of people in set A intersect B, right? So let's identify what we want. We want the number of people in A intersect B. Now we have a formula that involves this number. Let's see if we can use that to find this amount. Here's our formula. Number of elements. Let me just sequester this information just to make the board easier to use. And I'll use the word recall. The number of elements in A union B, that's equal to the number of elements in set A plus the number of elements in set B. And then we have to have our correction term minus the number of people in A intersect B. And oddly enough, this is exactly what we want. Now let's fill in the blanks. The number of people in A union B. A union people are those who had pecan pie or sweet potato pie or both. So in other words, this is all of the people who had dessert. and that's 86 customers. And A, those are the people who had pecan pie, so that's 53. And B, that's sweet potato pie. 48 had sweet potato pie. That's the number of people in set B. Okay. So here's what we have. I'm going to explain this arrow right after I finish this exercise. Here's what we have. 86 equals 53 plus 48 minus the thing that we want, A intersect B. I'm going to get this by itself. I'm going to add this to both sides. And so that will give me number of people in set A and B plus 86 equals 53 plus 48. And this is what I want. So I'm going to get this 86 on the other side. I'm going to subtract it. So that leaves me with number of people in A intersect B equals 53 plus 48 minus 86 oh goodness gracious. Let's see. What is this, 101? So this means that we have number of people in A and B equals 101 minus 86, so that's 15. And that's what we want. So that's an example of how we can use the counting formula. And we want to be very good at using the counting formula because this is going to come into play when we do probability. Doesn't seem like there really should be a connection between the two, but there is. So we want to get very comfortable using the formula that I just erased. Let's see, what was that? Number of elements in A union B equals number of elements in set A plus the number of elements in set B minus the number of elements in the intersection. We want to get very good at using this formula. We're going to see it outside of our study of sets. We're going to see this when we study probability. And hopefully by that time, this kind of thinking will be second nature to us. And so we'll be very ready to understand how we apply this to probability problems. This concludes our lecture for, it's Thursday, isn't it? Thursday.